Hi guys, and welcome again to Misostudy session of lectures on differential equations. In the recent lectures, we started discussing about the new head, which is homogeneous differential equations. Homogeneous differential equations. One can understand homogeneous differential equations only when he or she has completely understood what is a homogeneous function. A homogeneous function in two variables x and y is such a function such that when you replace x by lambda x and y by lambda y, f of lambda x comma lambda y turns out to be lambda to the power n fxy. When you can extract lambda out of f of lambda x comma lambda y with a certain power which is a non-negative integer, you say f is a homogeneous function of that particular integral degree. Understood? So, if f of lambda x comma lambda y is lambda to the power n f of x comma y, you say f is a homogeneous function of degree n. Understood? That particular definition of homogeneous function is what makes the definition of homogeneous differential equation. I told you that a differential equation of the form dy by dx, which is a first order first degree differential equation written in the form dy by dx equals phi of x comma y upon xi of x comma y, where this phi of x comma y is a homogeneous function of a certain degree, say n, and this function xi is also homogeneous function of same degree n. If your differential equation is expressible in this form, where this is completely a rational function with numerator as a homogeneous function of degree n and denominator function as again a homogeneous function of the same degree n, then such a differential equation is what is called a homogeneous differential equation. I told you to solve a homogeneous differential equation, first step is to identify whether a differential equation is homogeneous or not. If you have completely identified that your given differential equation of first order and first degree is a homogeneous differential equation written in this form, the next step will be what? First identification is done. Our very target is to convert the homogeneous differential equation into the variable separable form. From homogeneous to variable separable, what is that one thing which makes this process possible? So, if you are at this stage that you have a homogeneous differential equation and somehow you want to convert it to the variable separable form, because you know how to solve variable separable form. Once the variables are completely separated, two variables completely separated, I can integrate both the sides with respect to the first variable and with respect to the second variable here and get my solution. So, variable separable form, if we are able to convert it into, we are very in a comfortable position. But how to from homogeneous come to variable separable? What is going to help us is the tool of substitution. How can we substitute and what should we substitute? We will be substituting y equals Vx in our given homogeneous differential equation. When you substitute y equals Vx in the given homogeneous differential equation, what happens is, when you differentiate both sides with respect to x, because this is your dependent variable and this is your independent variable. So differentiate both sides with respect to the independent variable x. What you get is dy by dx equals, now v is also the new variable introduced, it's a function of x. Over here we are going to apply the product rule. What is d by dx of v into x? D by dx of v into x plus d by dx of x into v. First term into differentiation of second plus second term differentiation of the first, which implies I am going to have dy by dx equals v plus dv by dx. So when you substitute y equals vx, what you get is your dy by dx in the homogeneous differential equation gets converted to v plus x into dv by dx. See, v plus x into dv by dx. You also have another option of substitution. As I told you, you can even go for substituting x equals vy. But in this situation, your x will be the dependent variable and y will be the independent variable. Your v will be the new variable introduced, will be treated as a function of y. So you have x equals vy. You differentiate with respect to the independent variable. Differentiating both sides with respect to y, what you get is dx by dy equals d by dy of vy. Product rule again, because v is a function of y. This is dx by dy equals first term into d by dy of y plus y d by dy of v, and so you get dx by dy equals v, d by dy of y is 1 plus y into dv by dy. So whenever you proceed with substituting x equals vy, you basically get the substitution for dx by dy. And when you substitute y equals vx, you get the substitution for dy by dx. Understood? What is it that basically this particular term helps in getting the variable separable form? How, when I substitute y equals vx or x equals vy, thereby changing my dependent variable from y to v and from x to v, when I do these substitutions, how do these changes, which eventually come and change my differential coefficients, affect my transformation from homogeneous to variable separable? Let's see. Well, if in general I try to understand, if suppose this is my given homogeneous differential equation, dy by dx equals phi xy upon xi xy, where phi and xi are homogeneous functions of exact same degree. After that, how should we proceed so that this substitution and the corresponding changes help me to convert it into the variable separable form? How should we actually proceed? Let's try to understand. So we have this. What is it that you have? dy by dx equals phi xy upon xi xy. Once you have this, and both phi and xi are homogeneous functions of degree n, what did I tell you? I had told you already that if phi of x comma y, or I should say, I told you when f of x comma y is homogeneous function of degree n, then I can always write f of x comma y as x to the power n into some function of y by x, or I can write f of x comma y as y to the power n, where n is the degree, into some function of x by y. Keep this very nicely in your mind, because this is what helps us in transforming homogeneous differential equation into variable separable form. See, phi is a homogeneous function of degree n. So, I can write it as x to the power n into some function of y by x. X to the power n into, say, phi 1 of y by x, some new function of y by x. Because xi is also a homogeneous function of the same degree n, I can write it as again x to the power n, say xi 1 of y by x. This is my dy by dx. I am transforming. Understand carefully, from this step I have come to this step by usage of this observation. Fine. So, phi of x comma y can be written as x to the power n phi 1 of y by x, and xi of x comma y can be written as x to the power n into xi 1 of y by x. This gets cancelled. I am simplifying my RHS. Now my RHS is phi 1 of y by x upon xi 1 of y by x, or I can say f of y by x. Because xi 1 upon phi 1 both are functions of y by x, so eventually this complete thing is a function of y by x, equals dy by dx. Fine. Now what you have is, this implies you are going to have dy by dx equals f of y by x. By this transformation, you will be eventually be able to convert from this differential equation to this differential equation, bringing y by x in picture. The moment y by x is brought into picture, obvious step is to substitute y by x equals v or y equals vx. So let's do that substitution. I am going to begin with substitution of y by x equals v or y equals vx. When in this equation you substitute y by x equals v or y equals vx, what is it that you get? As we just said, when you substitute y equals vx, y is dependent, x is independent, differentiate both sides with respect to the independent variable, what you get is dy by dx equals v into d by dx of x, which is 1, plus x into dv by dx. Understood? This is dy by dx equals v plus x into dv by dx. Once you have obtained this complete expression, go and substitute this and this in your original differential equation, that is the equation which we have marked as 1, which we transformed, which had y by x expression. Go and substitute v in place of y by x, and dy by dx will be replaced by v plus x dv by dx, because all in all we are trying to completely change our dependent variable from y to v. So therefore 1 becomes, this is 1, what is 1? dy by dx equals f of y by x. So what is your 1 becoming now? dy by dx will be converted to v plus x into dv by dx. This will be your left hand side, equals f of y by x will now be f of v. you will be having a function of v on the right hand side and v plus x into dv by dx on the left hand side always. You can easily take this v here and get what? When you take that v over here, you get x dv by dx equals f of v minus v. Now, f of v minus v is also completely a function of v only. I can put it together with dv and I can club all the elements containing x one side. So, here at this stage, I am able to separate all the terms or all the contents of v from all the contents of x. How? I can write this as, the first question is that the differential equation of all parabolas whose axis of symmetry is parallel to x axis is of order what? So, over here you need to understand that parabolas whose axis of symmetry is parallel to x axis have a general form of what? They are represented in general by x equals ay square plus by plus c. Now, the moment you have the equation of any parabola whose axis of symmetry is parallel to x axis, you can very easily see that a, b, c are three independent constants, and therefore, in order to get the differential equation, you will have to 3 times differentiate to basically eradicate the 3 independent constants, and that is going to give the degree to the differential equation to be 3, right? And therefore, the answer directly is 3. You don't need to evaluate the differential equation, no, you don't need to do that. Just remember the concept about independent constants. Those many times you will be differentiating to eradicate these constants, and that is going to give you the very degree. Next question says that the solution of the differential equation, now there is a differential equation given to you and the question is to compute its solution. So, let us do that. Dy by dx is equal to x square plus y square plus 1 upon 2xy. I can write this as 2xy dy being equal to x square plus 1 plus y square dx, right? Now see, this is 2xy dy minus y square dx equals x square plus 1 dx. Try to recall the formula of d of y by x, right? What was it? It was x dy minus y dx upon x square. Similarly, over here if you try to create the pattern, this is 2y dy which is actually d of y square minus y square d of x equals x square plus 1 dx. I want an x square over here in the denominator. If I divide both sides by x square, I get this upon x square and I get this upon x square. This becomes what? X dy minus y dx whole upon x square is d of y by x. Y is replaced by y square, you get d of y square by x. This is equal to what? 1 plus 1 by x square dx, or I can write it as d of x minus 1 by x, right? D of x minus 1 by x is nothing but 1 plus 1 by x square dx. Again, when you integrate both sides, you obviously get y square by x equals x minus 1 by x plus the constant of integration. And over here you get y square equals x square minus 1 plus cx, which you can write it as x square plus cx plus c by 2 whole square minus 1 minus c by 2 whole square. I am just completing the square. This is x plus c by 2 whole square minus 1 minus c square by 4. This obviously is representing a hyperbola, and therefore the solution is basically a hyperbola. Clear? That's how easily, just by the usage of this particular formula, that d of y by x is x dy minus y dx upon x square, I was able to accomplish the result. Next question says what? It is asking you to compute the integrating factor of this differential equation. Let's do that. So obviously, this is a linear differential equation and that is why the question is asking us to get the integrating factor. I am going to rewrite this as dy by dx plus minus x upon 1 minus x square y equals 1 upon 1 minus x square. Dy by dx plus py equals q, where p and q is function of x. Integrating factor is e to the power integration of p dx, e to the power integration of minus x upon 1 minus x square dx. Let's separately see this. If I take 1 minus x square as t, this gives me minus 2x dx is dt, and I get x dx is minus dt by 2. So x dx will be minus dt by 2, and denominator is t. So you get minus 1 by 2 ln t. What you get? Minus 1 by 2 ln t, which is minus 1 by 2 ln of 1 minus x square, because 1 minus x square was t, and therefore what is it that you get? You get minus root over 1 minus x square. No, ln of, this is ln of minus root over 1 minus x square. Why? Because minus 1 by 2 is going to go over here. Let me say 1 by 2 is going to go over here. That is going to be 1 minus x square to the power 1 by 2, which is root of this, and this is going to be minus ln this. Now the moment you plug this value again over here, you have e to the power. This complete integration is this, minus into minus becomes plus. You are left with ln of root over 1 minus x square, which is obviously root over 1 minus x square. And therefore your answer is option number C. Clear? Very, very easy, direct, very computation of the integrating factor. Orthogonal trajectories. Okay. So the orthogonal trajectories of the family of curves given by y equals cx square. Okay. So what is the way to actually compute the orthogonal trajectories? Y is given to be equal to cx square. Differentiate both sides with respect to x. You get this. From here get the value of c, it is 1 by 2x dy by dx. C is 1 by 2x dy by dx. Plug this value over here, you get y equals 1 by 2x dy by dx into x square. This gives you x by 2 dy by dx, that is 2y equals x dy by dx. Now this is the differential equation which is representing this family of curves. I don't want the differential equation, I want the orthogonal trajectory. So the algorithm says that once you have the differential equation representing the family of curves, replace dy by dx by minus dx by dy. So you are going to get minus dx by dy. So from here you get 2y dy equals minus x dx. Integrate, you get y square by 2. So 2 gets cancelled, equals minus x square by 2, right, plus c. So this gives you 2y square plus x square. Why? Because I bring it over here, I get 2y square plus x square equals 2c. Let's see. 2y square plus x square equals 2c. This is the very equation for the orthogonal trajectories of the family of curves represented by y equals cx square. Simple algorithm, I just applied the algorithm and got my answer. So if the algorithm is not clear to you, you won't be able to accomplish the result. Next question says the degree of this differential equation is what? Now see, in a bit complex form this particular differential equation is given to you, but this differential equation is actually representing the series e to the power x. E to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. In place of x there is dy by dx, and therefore I can write this as x equals e to the power dy by dx. Taking log both sides, I get log x equals log of e to the power dy by dx, which is just this, And clearly you can see this is a differential equation of degree 1 and therefore answer is this. Just keep in mind that e to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. In place of x, if I put dy by dx, I get the exact same thing which is written over here. Fine. Now I have the next question, which is that the differential equation of all circles. Now special type of circles are there. They are